All right, so the last section this week is going to talk about connectivity verification. This is typically using ICMP or your ping and traceroute utilities. We've kind of mentioned those a little bit in the last two sections. So ICMP is part of a TCP/IP protocol suite, and this is used to send error messages or test messages, etc. The purpose of these messages is to provide feedback to issues related in processing those IP packets under certain conditions. ICMP messages are not required and are often not allowed on a network for security reasons. So if you start seeing a bunch of ICMP traffic on your network, you may want to take a look at that as a cybersecurity analyst. It's available for both IPv4 and IPv6. It's a messaging protocol for IPv4. IPv6 provides some services similar to that, but includes additional functionality. ICMP messages are common to both IPv4 and v6, host confirmation, destination, service unreachable, time exceeded, and route direction. Basically, these are going to be your pings. So host for information, when you send a ping, you are sending a ICMP echo message. And so it says, is H2 available or reachable? And so therefore we're going to try to ping the IP address of this over here. It sends an echo request. And as that traffics through the network, if a address over here is listening on that one, it says, yes, I'm here, and then sends a reply packet going back. So you'll see that come through there. A destination or service unreachable, this is typically because it can't deliver that. So either that host is unreachable, which is a number 1 code. A protocol is having an issue. It's a number 2. The particular port you're trying to access is 3. And then just the entire network's unreachable is a 0. You can also have TTLs, or your time has been exceeded. So every packet that you send out typically has a TTL. And as it goes through a different hop or a different time increment, it ends up getting decremented to the 0. Once it hits 0, the packets end up dropping and it's discarded by the next one that goes through there. So the time to live is typically there just to make sure that that packet isn't floating out on the network and chewing up resources if it has no place to go. Note that IPv6 does not have a TTL field. Instead, it uses a hop limit field in order to determine if the packet has expired. So this one's based on time. IPv6 is based on the number of hops that has to go through in order for it to be delivered. In IPv6, you have new features to improve based on what's on IPv4. This is starting with new protocols such as Network Discovery Protocol to see what's all on the network. The messaging between the router and the device is typically you have a router solicitation message along with a router advertisement message. And the messaging between devices is usually neighbor solicitations and neighbor advertisements. So in an IPv6 network, it's a little different. With a router solicitation, you're going to have messaging between the router and the device itself. For example, what you saw with my IP addressing there. And you're going to use stateless auto configuration. So Slack is very similar to DHCP, but this allows you to get some auto configuration of your addressing. The router will send an RA message periodically and in response to an RS message. So for example, all IPv addresses are multicasted out, and then these are all responding with a multicast going back telling it what router it is. So I just boot it up and I will send an RS to request an RA, and then it comes back this direction. Address resolution, this is again messaging in an IPv6 area. These are called NA messages, and this is again your neighbor advertisement message. So when a device is known to have an IPv6 of a device but doesn't know its MAC address, this is similar to an ARP request on IPv4. So be familiar with what the equivalent is between the two protocols. NA messages are sent in response to an NS and match the target IPv6 address in the NS. So an NA message is going to include the device's Ethernet MAC address, which is equivalent to an ARP reply. So difference between IPv4 and IPv6 when dealing with address resolution. In IPv4, we use ARP, which is address response protocol. Yeah. And then in your IPv6, you're going to have NA and NS messages going between there. So neighbor advertisements and neighbor solicitations. You could also have duplicate address detection, or DAD. Know that acronym. DAD is performed on the address to ensure that it's unique. Everybody on a network must have a unique address. And so, for example, this little host here is going to say, let me make sure my IPv address is unique. Whoever has this address, send me your MAC address. If I don't get an NA back, then my IPv address must be unique. So when this thing comes online, it says, hey, here's my IP address. Does anybody else have that? As you can see here, you can get a not me, not me, not me. They are not sending this messages back, right? The only time it would send a message back is if it actually has a response. Otherwise, we'd be flooding the network with a bunch of traffic. All right, two main tools that you guys will use, ping and traceroute. We talked about this in the very beginning. So you guys will have some labs going across this. Ping is a great tool in order to test IPv4 connectivity. It uses ICMP echo repackets and replies in order to test connectivity. But just because something doesn't respond to a ping doesn't mean necessarily that the host is down. It could just be filtering out ICMP traffic. And the reason it would do that is you may not want to respond to a ping request and be live. So a lot of time your servers and such like that don't necessarily respond to ping requests. As a matter of fact, your laptop by default, if you got the Windows firewall running, you will not hear ping echoes and responses. So if you guys ever try to ping on your local network and don't get it to work, more than likely that firewall is blocking those ICMP requests. So the ping utility, be familiar with that. You guys will do this in a lab, but you can use it to typically test your default gateway. So on a home network, if I want to test to make sure that I have access to my default gateway, I can do a ping 192.168.1.1, and we can see that my router in this case is responding back with that address. In this ICMP packet, we're going to see that these are little 32-bit packets. It takes 2 milliseconds and then up to 1 millisecond. Notice it goes clear down to less than a millisecond. That's because I have a direct wire going from me all the way out to that router. There's actually a hop initially between there. There's a switch, there's a second switch, and then it gets to the router, which is actually a firewall. And we can see those time to lives. And some other switches that you can use here is a -T. -T is going to go on indefinitely. This allows you to test this, and then I can pull the cable, and then I can see that those packets are going to start dropping. What's nice here is the statistics. So if you're starting to have issues in connectivity and it's dropping, you may look at how many were sent, how many was received, and how much loss was actually going on. On wired-based Ethernets, you really should not see a whole lot of stuff over here unless you've got a bad switch or a bad port, bad cable, etc. But on a wireless network, you may see some drop in some packets here. Again, I can ping my default gateway. I can ping out to Google. And notice how Google responds with a reply. This is their DNS section here. And you can see that they only have a 18 millisecond delay, which from my house it's pretty good latency that's going in between there. You can send larger packets if you want to. So there's a lot of different flags that you can set with the ping utility. So if I do ping-h, I can see all these different sizes that go through. I can see whether I can resolve IP addresses out to host names. You can force IPv4 or IPv6 to respond there. You can set a bunch of stuff. So for example, if I want to use, let's see here, if I use ping-l is going to be my size, the buffer size that I want to send, and I'm going to send 1500 size packets out, and I want to send 4 of those out there. Oh, and I gotta send the IP address. So if I send this out to my firewall, we're going to see that those byte sizes are now a full 1500 going across the frame, and then we're going to see 1 millisecond delays there. Now, as you increase those byte sizes, obviously these packet size can corrupt. So if I go through here and set this as a 9,000 byte packet, no, it does send it because I have jumbo frame enabled between those two, but a lot of times this will start corrupting. As you get larger and larger packets, it's not able to send it out. Notice that you have an increase in latency by sending larger packets across the wire. So if I get crazy and I do something like 9 million, let's see, oh, it's got to stick within the 655, okay. So if we do the 65500, Notice here, my router won't even respond to this packet size. The request just times out. And that's because something along the way is seeing this large of a packet go through and it's dropping that packet. So this could be one of my switches. This could be my firewall itself. Something's blocking that. And if we were to play with this a little bit, we could probably find out that 10,000 packets, notice those are still going through. See if we can find a breaking point here. All right, 20,000, we're up to 2 milliseconds of latency. Now we're up to 3 milliseconds. This will eventually get to a point where it cannot handle it anywhere in between. So notice we jumped clear up to 7 there for a little bit. So as you'll notice, your packet size is inversely proportional to the time it takes for that to traffic over the network. And I'm going to get larger packet sizes until eventually it's just going to die. So if I send this packet size, and obviously I can't send a 70 because that should be outside the range. Yeah. And let's see, 65. Notice it goes all the way through there. So if I try to max out that packet size, that's when I start getting those dropped packets. But I can definitely send some large packets through my network. You can always ping your loopback address. This just makes sure that your NIC card is up and running. So this is typically a 127.0.0.1 for your IPv4 networks or a : :1 for your IPv6. So again, if I wanted to ping some IPv6 addressing or my IPv4, I could do ping 127.0.0.1. And that is my local address. I should see a very low TTL for those. As well as the time it takes for that to go. Note the TTL is a time to live is 128 seconds. Now I could tweak that too. So if I do something like ping-I and set my TTL to 1 millisecond, and then I'm going to go clear out to Google. Whoops. I did not mean to type the TTL there. You'll see that that packet expires. It takes more than 1 millisecond for it to get out there, and therefore that packet expires. So if I set that higher, for example, if I set it to 128, the default, or 129, it goes all the way through and it's fine to live. It's 117 is where it starts to fail. So if I set this to 110, you'll notice that it still made it through. It's at 18 millisecond delay. So if I set this to something like 10, it'll still barely make it through. And now it's going to time out within that 5 TTL. So ping is a great tool initially to test. Just know that just because something doesn't respond doesn't necessarily mean that that host is down. It's an initial test, but it doesn't necessarily mean that it's down. It just may not be allowed to respond to ICMP. So when you guys get into a little bit of hacking and network identification, you guys are going to use a tool called Nmap later on. And Nmap works by default by sending pings out and looking for replies. And that's just a quick and simple way to figure out everything that's on the network. So if I ping my default gateway, I can see that's out here. This one's set up, echo, reply, and request. I think we've covered that in pretty good detail. You can ping a remote host, which is what I did by pinging Google, and that's going to send you through the different networks and on out. If we want to see what those different networks are, we'll see the Traceroute utility or Traceroute. It depends on which operating system you're on. So if you are in Windows, it's going to be Traceroute. And we can do that here. And we want to see all the hops between me and Google, I will do a Traceroute. If I was on Linux, this would be Traceroute. So we'll notice that it took less than a millisecond to get to my local router, 192.168.1.1. It took a little bit of time in order to get out to my Nextech connection. Note that this one is going to their private network, which is an internal router within Nextech. From there, it goes out to a public IP address, which is going to be 242.251.9. Then it makes a hop out to their next router, 1.2. At that point, it's going to jump clear out to 4.34. And if we looked up these IP addressing, we could actually see who this is and where that's hopping out to. So if we take a bigger look out here and look up who is, and when we do a who is lookup, if you guys have never done who is, Who is going to allow you to figure out IP address space, and ICANN to figure out who owns what. So if I enter in, let's see, that's the domain name. That's not what I want. There we go. And if we look up 4.34.44.21, and a lot of times you'll get it translated, like what you see here with Nextech. It's translated those IPs to see who you're actually finding in those. But we make several hops going outbound here, and what's nice is you can trace these out. So notice the entire time it took to complete this, we can add up this column over here and figure out how long it took in order for that to end up showing out there. If something fails or times out along the way, so say I type in something that doesn't exist. So if I type if I try to trace route out to this, probably gonna die. Get to my router and die rather. All right, so notice this was a public IP address and it's accessible. It's going out here, 5. Okay, so now we started to get some stars, which means when it got to this router, it didn't know how to get to the next router, and we started getting requests timed out from this point on. So once it hit their gateway router at Nextech, it didn't know how to necessarily get out to this IP address. But because my default gateway was set to my local router, and then the default gateway for that router was set to here, default gateway here, and here, once it got to here, there was no default gateway that was going to start responding to this. And so this will keep going until it just request times out and we lose that traffic. So again, if we look up something like 4.34.44.21, and there's all sorts of tools out there who will tell you these lookups. So like here, I just did a lookup on the next hop there, that 4.34.44.21, and we'll notice that this is level 3. So of the uplinks that Nextech has, it's going out to level 3. And then we can trace route out and find out who owns 72.14.221.18. And then level 3 ends up connecting out to Google. And so then it's trafficking out to Google's network, and which it should, right? Because we're trying to get out to Google's network. Then it bounces through a couple Google hops until it ends up getting to their DNS server. So Traceroute's a very powerful tool. You guys will definitely use that in between there. You'll notice that the asterisk, as we demonstrated before, is used to indicate a lost packet or something that didn't reply. So it didn't necessarily get lost at that point. It's just all those routers and things that are out there were set not to reply or kill ICMP traffic. You can show the high response times. You can also see the low response times and the average response times. So again, with IPv4, you have a TTL. With IPv6, you have a hop limit, and this is going to dictate the different fields and when that message is going to expire. And at a certain point, it will expire. You can see this with an ICMP packet format. So again, a 0, when we send ICMP packets of 0, this is a reply to a response on a ping. Echo request for a ping is an 8. Destination unreachable is a 3, redirect to 5, and then time exceeded became your 11s. So if we wanted to flood a bunch of packets or pings everywhere, we could do that, causing a host to have to respond to all those, especially if they have the packets turned on, which is basically referring to a small level denial of service, right? If I can send enough packets to you fast enough and just flood your network with those packets, I can chew up all the traffic on your network. I can also slow down your overall internet connection. So just like what we were doing before, where we were sending massive packets out on my network, we will notice if I do a ping 192.168.1.1 and do a -t, this is only sending 32 byte packets. And if we were to look at my traffic that's going out on my network, Give me just a second for it to load up here. All right, so if we look at my network traffic as it's going out, you notice that I have traffic going out. Now, obviously, I'm doing this recording on this live Zoom, so you're going to see some traffic going out, but note that it's really not dramatic as to what's going out there. Let me send that. Now, if I go ahead and kill this, okay, and this time I'm going to do a -L, and I'm going to set this to 65,000. Notice that I have a huge jump in traffic that's going out there. Now, is this killing my network connection? No. I mean, I'm only generating roughly about a meg of traffic at times. It looks like it peaked at one point to that. Notice that these pings are waiting for a reply on each one of those. Now, if I send out a whole bunch of pings all at once, I can actually flood the network pretty good and generate quite a bit more traffic. So you'll notice now I have this constant flat rate of me sending all these pings out, and it's enough to go through there. If we calculate up 65,000 bytes and then start calculating that up, we can figure that out how many kilobytes that would end up being out here. So that's what, 65 kilobytes for each one of those packets, and then it starts generating more and more traffic out all the time. With this standard ping utility, I don't think we can set the rate that we want to go through there. Let's see here. Time to live. Yeah, so here's the other one. We were sending packets earlier, but I forgot to send the don't fragment one. So if I send a -L and I say 1500 and I say don't fragment these packets, you'll notice that it has to be fragmented. Why? Because my network won't allow 1500 byte packets to be sent. I would have to send something significantly smaller in order for that to work. So say a 64-bit or 34-bit packet, I can send those out and I won't fragment that. And that will allow me to send that. So I'm sending those 65,000 size bytes out there. It's actually fragmenting that into a bunch of different packets and then sending all those replies back from each one of those to make sure that that works. Let's see. I was hoping, don't think you can do that where you can flood that out with the standard ping utility. You have to use a third-party utility in order to do that. So ignore me on that side. Okay. Packet Tracer, there's some Packet Tracer labs. Again, I don't push the Packet Tracer labs in here, but if you guys want to test those, you can do some pings and some tracerts to test that around. You can also do a lab on NetLab that will go through and test this kind of thing as well. So when doing connectivity verification testing, you can use ICMP packets to test whether IPv4 or IPv6 is hitting forwarding problems. ICMP is the messaging protocol for IPv4, and ICMPv6 is for 6. 6 has some extra features. For example, it allows you to do network discovery as well as send router solicitations and router advertisements. Remember that that's between a router and a host, and the neighbor solicitations and neighbor advertisements are between IPv6 hosts. Ping is a great utility. It'll initially send an echo request, and then a host will either send an echo reply. You could also have other codes that can be sent back if that connectivity is not able to be reached. All right, so that should cover the highlights of this particular section on connectivity. Make sure to complete your labs, and you guys will get to play with that a little bit more and see how that works.